Hi students, good evening to all of you. And today is session 5 in our series of digital sum up. Can you confirm me whether this audio, video, everything is fine or not in the chat box? And then immediately we'll start today's session. Okay. So well, in the last class, we have completed the sequencer circuit, isn't it? Sorry, the combinatorial circuits. And today we are going to take the most important topic of the entire digital, that is the sequencer circuits. Although the sequencer circuits is the biggest chapters among all in the digital, but again there are some areas from where questions are targeted. So in particular, in this case, so these are the 4 models I have written here. One is the latch. Next one is the flip-flop. And in flip-flop, based on the conversions and some other property questions are being targeted. The third category is the shift register. Okay. And the fourth category is the counters. In counters, again, there are analysis and synthesis. There are 2 segments basically, isn't it? So this is what we are going to see today. Okay. So let me give you a quick overview, okay, of the latch. And then again in the as usual pattern, so we'll be switching into the question segments. Well, latch is a 1-bit memory elements. Okay. So what is the standard thing that all of you might have studied in the theory is the SR NAND latch and the SR NOR latch. Do remember, these are 2 circuits where this is Q and this is Q bar, this is Q bar and this is Q. But this pattern which I have written here, this Q bar or Q bar Q pattern, that may not be uniform in all questions. Okay. So it is wise to understand the properties. What you need to understand is, if one of the input to NAND gate is 0, the corresponding output is 1. If one of the input to NOR gate is 1, the corresponding output is basically 0. So based on that, majority of the cases you can understand. So this is the corresponding truth table of both cases I have given. So you can see this is for the SR NAND latch. So when it is 0, 0, so 0, 0 case, we get Q plus and Q plus complements are 1, which is invalid states. And if it is 1, 1, then Q plus equals to the previous state. So we say it is in memory states. So in case of SR NAND latch, when the input is 0, 0, the corresponding output is 1, 1, which is invalid. But if the input is 1 and 1, the corresponding output is the previous state. So we say it is in memory states. And if the input is 0, 1, okay, if the input is 0, and if I give this is 0, this is 1. So this is 1, and this will be complement to it, it is 0. But if I give this is 1, 0, so if this is 0, this is what 1. If this is 1, this will be its complement, that is 0. So same is the story for this NOR latch case as well. In this case, if you make both of the input 1, 1, you get 0, 0. We say it is invalid. If I make this is 0, 0, we say it is in memory states. But if I make this is 0, this is 1. If this is 1, this is 0. And if this is 0, this is 1. And similarly, if I make this is 1, this is 0. So because this is 1, so this is 0. If this is 0, this will be 1. So very simple. Okay. So that is what, how do you understand or how do you memorize the property? So this is what is the truth table, which is valid with respect to these notations. But again, I'm reminding you in the corresponding gate exam or any other exams. So this notation, you should be very, very careful. Sometimes they may give you this is X, this is Y, this is F1, this is F2, this kind of things. So you should observe the question carefully and accordingly you should proceed. Here is one important point from where majority of the questions are targeted in the last couple of years. Remember, so here in case of this, okay, this NAND latch case, okay, in case of the NAND latch case, so this is what I have written something called special case. If the input sequence is 0, 0 followed by 1, 1, that is the input corresponds to memory state followed by the invalid state. Then the next state output will be fluctuation if the delay of both gates are same. Otherwise, it is unpredictable. I mean, sometime it can be 0, sometime it will be 1. So what I mean is, if I'm giving first 0, 0, and then after some time I'm changing it to 1, 1. So in this sequence, 0, 0 followed by 1, 1 sequence, then what is the next state output we cannot tell. So remember always, if the input is corresponds to memory state followed by invalid state, then the next state is unpredictable. It depends on the delay. So this is 0, 0 is the corresponding invalid state here. 1, 1 is the memory state. But here it is opposite. That is 1, 1 is invalid and 0, 0 is memory state. So in case of NAND, 0, 0 followed by 1, 1, it matters. In case of NOR, 1, 1 followed by 0, 0, it matters. In these cases, you'll get the unpredictable output. That is why we are calling it a sequential circuit. In what sequence you give the input, it does matter. So this is what all about your latch. So if you get any questions in the GATE exams, so 90% of the cases, 100% of the cases till today, okay. So all the questions from latch are targeted from either from this circuit or from this circuit. And if you know its corresponding truth table and the special cases, all questions you can answer. So I have designed one question for you, and let me see how many of you are able to answer this properly. So here is the question, okay. So this is a circuit I have given. If x1, x2 sequence is 0, 1 followed by 1, 1 followed by 0, 0, then the corresponding f1, f2 sequence is. So this is what my f1 and this is what my f2 is. Yes, who can answer this? So I mean, that's what I'm saying. You need to have the good analysis skill, okay? I mean, you cannot expect always you'll be getting the standard circuits. You'll be saying, okay, so this circuit we haven't studied in our classroom. How do you answer it? That is a nonsense, logic if you say this way. So let me see how many of you are able to tell this answer properly. So here, what I can do is I'm making a table by taking x1, x2, and f1, f2. I mean, to be very specific, f1 plus and f2 plus. So I want to make a table because here I need with respect to 0, 1 and then 1, 1 and 0, 0. I need to check if 0, 1 is the input, what is the next state output? 1, 1 is the input, what is the next state outputs? 0, 0 is the input, what is the next state outputs? That's what I need to check. If I can tell that, then this problem is over. So for this, I'm copying this again. Okay. So coming to the first case, the input I want to give is 0, 1. See here, I want to give the input 0, 1. So this is 0 and this is 1. You know very well, okay, if the input is 0, 1, so if one of the input to AND gate, this is an AND gate and this is an OR gate. So if one of the input is 0 to the AND gate, so compulsorily, irrespective of the other one, its output is 0. Similarly, 1 is the inputs to the OR gates. So irrespective of this inputs, so this output is 1. So what I can say is, if the input is 0, 1, so the corresponding next state value of f1 is 0 and f2 is 1. So remember, so this value which I'm writing, this is irrespective of its corresponding previous states. I mean, directly if I'm fixing it to 0, 1, it doesn't matter what is here and what is here. So this is what is the final steady state outputs. Well, having said that, so now let's go with the 1, 1. So if I'm giving the input 1, 1, then what's going to happen? So if I give the input 1, 1, if this is 1, then this is also 1. If this is 1, this is 1, and if both are 1, 1, this is also 1. Once again, I'm repeating. If this input is 1, I'm making, so irrespective of this, this is 1. If this is 1, that means this is also 1. And if this is 1 and this is 1, so 1, 1, so this is what is your 1. Okay. So what I can tell is, if the corresponding input is 1, 1, the corresponding next state is also 1. Okay. Now, next I want to give the input 0, 0. If I'm making this is 0 and this is 0, then what will happen? If I make both are 0, 0, if I make both are 0, 0, okay. So if this is 0, so its corresponding output is 0. If this is 0, this is also 0. And 0, 0 is the input to the OR gate, so this is also 0. So the corresponding output is 0, 0. Okay, the corresponding output is 0, 0. You are not supposed to be surprised, like how, sir, these are not coming complement to each other. That's what I'm saying. It is not a rule that like this and this will be always complement to each other. It may not, depends on the situation. Okay, so what I can tell is, so here if the input sequence is 0, 1, the corresponding next state is 0, 1. So for 0, 1, the next state is 0, 1. Then the input is 1, 1. So for 1, 1, we said the next state is again 1, 1. And then the input is 0, 0. And for 0, 0, we said it is 0, 0. So if the input sequence is this, then the corresponding sequence of F1, F2 is also same. 0, 1, 1, 1, and 0, 0. Why some people are getting 1, 0? I mean, Kusagra, Anushka, Mayank, I mean, Soumya, what are these? How you are getting 1, 0 at the end? In my opinion, it should be 0, 0. See, how I got 0, 0, once again, let me explain if you are getting doubts. So, how I got 0, 0 in the sense, if I'm giving this is 0 and this is 0, you tell if this is 0, then irrespective of this, the corresponding output is basically 0. Now, if this is 0, so this is also 0, right? And if the 0 and 0 is the input to the OR gates, the corresponding output is 0. So from where 1 will come, it is the 0 only. So 0, 1 followed by 1, 1 followed by 0, 0 is the right answer. So this is what is the only question I have taken from the latch. Okay. And so next we'll be switching into the corresponding flip-flop topic. So in the flip-flop, okay, so we attach some kind of clock signal in the latch. So the corresponding circuit is the flip-flops. So we have basically 4 kind of standard flip-flop, namely SR, JK, T, and D. There are 4 kind of standard flip-flop. Although there can be n number of different flip-flop possible, but yes, in general we have 4 kind of standard flip-flop. Remember, any particular flip-flop is associated with 3 kind of tables. One is the truth table, one is the characteristic table, and the third one is excitation table. Okay, so in characteristics table, what we do is, if in the this is what, let's say for example SR flip-flop. So this is what is the truth table. And what is the state table? State table means we have the SR and the present state. So based on the flip-flop input and present state, we are finding the next state. That is what is the characteristics table. And suppose we know the present state and the next state, that is Q and Q plus is known to us, but I have to get this SR. In such kind of cases, we go with excitation table. Like here, I have Q and Q plus known. I want to get what is S and R. So here I'll be going with excitation table. So these are 3 kind of tables. So you'll be always making use of this one. Okay. So in the counter also we'll begin using this. So it is always wise to memorize the corresponding circuit diagrams and all the 3 tables. So for the SR flip-flop, you can see. So 0, 0 is the input. Next state is the same state. 0, 1 means next state is 0. 1, 0 means 1. And 1, 1 means it is invalid state. If you make it is 1, 1. So in that case, Q and Q bar happens to be same. It can be 0, 0 or it can be 1, 1, depending on what kind of latch is there. But if the input is 1, 1, so Q and Q bar, they are same. So that's why we call this is invalid state in case of SR flip-flop. So this is what is the corresponding state table. So I'm not going into very detail of it, but what I will suggest is to memorize the corresponding characteristic equation. So for the SR flip-flop, the equation is S plus R bar Q. And whatever is there in this corresponding state table, if I'm representing in the form of a diagram, this is what I'm calling it the state diagram of the SR flip-flop. So suppose if somebody asks me, so what is the meaning of this particular line? In other words, what is the meaning of this line? If somebody asks me, it means if the present state is 0, if the input is 1 and 0, the next state is 1. So if the input is 1, 0, present state is 0, next state is 1. That means this particular row is represented by this particular line. So like this, we have 8 rows. You can see here, there are 8 representation. 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So like this, we have the truth table, we have the state table, we have the state equation, state diagram, and this is what the excitation table. Okay. So in the theory, you must have learned this, how to derive the excitation table from the state table and all. So next is the JK flip-flop. So in the JK flip-flop, this is what the truth table. So the only change here is, here it is Q equals to Q bar we are getting in case of 1, 1. But in the JK flip-flop case, we'll be getting Q plus equals to Q bar. I mean, this is the only change, the last row is changing. That's all. State equation is given by J Q bar plus K bar Q. Okay, and this is the same table if I'm representing the form of a diagram. So this is how it will look like. And if you want, you may take a screenshot or you may have your own. Anyway, this document is also with you, right? The students who are our annual students, the handbook is with you. So this is what is the corresponding excitation table. So in the T flip-flop, what we do is we sort this J and K terminal and we say this is the T flip-flop. So if the T input is 0, Q plus equals to Q. If T input is 1, Q plus equals to Q bar. Now, why I'm discussing in such a way is because if you see the gate questions, sometimes very direct question they're asking. Which of the following is the characteristic equation of the JK flip-flop? Which of the following is the state diagram of this, that? So like that questions are also being asked. So just like this is part of theory. And you need this particular theory to answer some tricky questions. That's why in a very quicker manner, I'm just revising your concepts. Okay. And the state equation is Tx or Q for T flip-flop. And this is the state table, state diagram. And this is what your excitation table is. So this is what your delay flip-flop. So delay flip-flop Q plus equals to D, right? And this is the state diagram and this is the excitation table. So concept of triggering, there are two kinds of triggering. Level triggering, it can be positive level or negative level. Similarly, we have edge triggering, positive edge or negative edge triggering. So it actually, what is the meaning of triggering is, in what duration or what instant of the clock cycle, the circuit should respond to the inputs. If I'm saying it's a positive edge triggering flip-flop, that means only when these edges are hitting to this particular terminal, this circuit will respond with respect to this and this input. So that's what the meaning of this thing is. So next is coming to this preset and clear input of the flip-flop. So very simple and straightforward. So preset is meant for initializing the flip-flop output to 1. If we make preset high, in this case, if I make preset 1, so it will make sure this is 1. If this is 1, that means this is 0. Okay, and if I want to initialize the initial state to 0, I'll be giving an activation signal on clear pin because it's an active high pin. So I'll be making here 1. If I make here 1, you get here 0, and this is what your 1 is. So what is the difference between this and this diagram? It is almost same. The only change is here, this is active high pin, but here it is active low pin. So you have to see the corresponding circuits carefully. So whether it is active high or it is active low. So in this case, you see here, so because it's active low, if I'm giving here 0, then preset is activated, you will get here 1 and this is 0. But if I give this is 0, that means this is 0 and this is 1. So this is what is the function of the preset and the clear. And one more bit questions that is possible is 2-3 times it has been asked, and from last couple of years they haven't asked. So the race around conditions. Remember, so race around condition, when does it happen is there are some conditions. The flip-flop should be of level triggered, not edge triggered. Okay. Input of the flip-flop should be in such a way that it will satisfy Q plus equals to Q bar. That means you should give the input in such a way that the flip-flop will be operated in the toggling mode. Okay, like for JK flip-flop, J equals to K equals to 1, and for T flip-flop, T equals to 1. And if the delay of the flip-flop is less than on period of the clock, then you get some toggling continuously in the outputs. So we say it is in the race around conditions. To avoid the race around conditions, so one of the solution is we should use the edge triggering flip-flop instead of level triggering. Second one is you should maintain this condition. The on period of the clock is less than the delay of the flip-flop is less than the overall clock. Otherwise, you should go with the master-slave configurations. So having said this, then we come into this conversion of the flip-flop. Okay, so what is the need of the conversion of the flip-flop? Like you may have a situations like you have a SR flip-flop, but you need a JK flip-flop, or you have a JK flip-flop, you need a D flip-flop. So how to convert a particular flip-flop, okay, existing flip-flop into some desired flip-flop. So that is what we mean by the conversion of the flip-flop. So you have 3 simple steps. Write the state table of the required flip-flop. Considering Q plus of step 1, write excitation table of given flip-flop. Using K-map, solve for given flip-flop input in terms of required flip-flop inputs and Q, and implement the circuits. So first 3 steps are sufficient to convert one flip-flop to other flip-flop. And based on this, I have taken this particular questions. The question is convert SR flip-flop into XY flip-flop. So what is the meaning of it? So that means, okay, what flip-flop I have? I have a SR flip-flop. So I have to convert this SR flip-flop into XY flip-flop. So you have to use some particular circuitry. Okay. So, so you have some combinator circuit here. You have some combinator circuit here. Okay. But ultimately, I want to see this is a XY flip-flop. So this is what your Q is. This is what your Q complement is. So you have this SR flip-flop given, and you want to make this is XY flip-flop. That is what my requirement is. So basically, you have to tell me what should be connected to S and what should be connected to R. So what is here and what is here. So based on that, you can tell, oh, what is the 6. So sequence circuit is tough. No, man, it is not tough. Hmm. 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 How? Anyone got any answer? So you have to follow those 3 simple steps, what I said. So using that, you can reach the answer. I'm giving you 2 minutes of time, and you have to give the corresponding answer within this much of time. So here, so the first step is write the state table of the required flip-flop, isn't it? So write the state table of the required flip-flop. So what is the required flip-flop here in this case? So the required flip-flop in this case is XY flip-flop. So you have to write the state table of this XY flip-flop. So I'm making the state table X, Y, Q, and Q plus. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, na? So it says when it is, so from this you can learn also how to get the state table from the truth table. So first case 0, 0 means it is 1. So in the first 2 cases, 0, 0 is the input, so the next state is 1. 0, 1 means Q bar. So here X is 0, Y is 1, Q bar. So 0 is 1, 1 is 0. Next is Q. So 1, 0 means it is Q. So this is 0 and this is 1. 1, 1 means it is 0. So this is 0 and this is also 0. The last 2 cases. So this is what is the first step, right? Then what we need, then the second step, if you see, so this step is over. Step 2, considering Q plus of step 1, write the excitation table of the given flip-flop. So you have to make use of the excitation table of the given flip-flop. So which flip-flop is given? SR flip-flop is given. So basically you need the excitation table of the given flip-flop. That's why I was telling you, memorizing all the table of the standard flip-flops are mandatory. So you need to refer this. So I am just copy this for your reference here. Okay. So let me put here. This is for S and this for R. See, so Q plus. So you have to consider Q and Q plus, and you have to refer this table and you have to fill it up. So Q plus is 0, 1. 0, 1 means it is 1, 0. So 1, 0. 1, 1. 1, 1 means it is don't care 0. So this is don't care, this is 0. Next is 0, 1. 0, 1 means again this combination 1, 0. 1, 0 means again it is 0, 1. 0, 1. 0, 0 means again 0 don't care. 1, 1 means don't care 0. 0, 0 means the first one again 0 don't care. And 1, 0 means it is 0, 1. Okay. So please use your K-map and tell me what is the answer you are getting. That is, what is S in terms of X, Y, Q, and what is R in terms of X, Y, Q? Yeah. So anybody who solved it? How much answer you're getting? So S, if I ask you what is the mean term, the mean terms are 0, I mean this row, then this row, that is 2 mean term. So let me write here. S, if I ask you what is in terms of X, Y, and Q, so it is mean term 0, comma, mean term 2. I mean, this is mean term 2, right? Then you have 0 and 2 only. Along with this, don't care combination, this one, that is 1. I mean, 1 and 5. 1, 5. Similarly, if I ask you what is R in terms of X, Y, and Q, so this, if you see, so there are again 2 mean terms, that is mean term 3 and the last row, that is mean term 7, plus don't care 4 and 6. 4 and 6. So now you have to solve through K-map. So this is, I mean, X bar, X, Y bar, Q bar, Y bar, Q, YQ, and YQ bar. So what are the mean term? Mean term 0, 1, 3, 2, and don't care 1 and 5. Don't care 1, don't care 5. So you have only one pair possible. So I can say here, this is a map, and the expression of S, in this case, you are getting this is X bar, Q bar. So X bar, Q bar is nothing but X plus Q whole complement. Similarly, you also try for R. So make a map again. So here you can get the expression of R. If you plot the map will look something like this. And if you try to find the expression of this R, so this R is coming as YQ. I mean the simple K map. Okay. So S we got. So if I ask you to design the corresponding circuits, so how does this circuit will look like? So how does this circuit look like in the sense? So it is SR flip-flop. So S input is nothing but how much we said X plus Q whole complement. That means I'm making a NOR gate here. So one of the input I'm giving from X, other input I'm giving it from Q. So this is your Q. So S is equals to X plus Q whole complements. It's a NOR gate. Similarly, R, if you see, so what is the expression of R we got? So expression of R is YQ. So one of the input is Y and other input is from Q. What your Q is. So all of you are in the same answer, right? Sir? Huh. कोई सरल है कुछ हो ना digamos contamos as onde usatório So R equals to YQ and S equals to X plus Q whole complements. Okay, so this is what is the question based on the flip-flop conversions. So we have seen a question based on the latch and flip-flop conversions and based on the property, I mean the standard informations. That is what we said. So next thing that we'd like to take up is a question which is based on the shift register. So here is the questions. So shift registers, only this model questions you can expect. So if you see the past history of papers, so only this model questions you'll get in the GATE exam from the shift register topic. Although there are many configuration SISO, SIPO, PISO, PIPO, etc. But this is what is the standard model actually. So for the registers shown below, how many clocks are needed to make it contain 1111? So please try to answer this. So what is the method for such kind of problems? We used to make a column called clock. Then we make something called inputs. And then we make something called next state. So next state means Q3 plus, Q2 plus, Q1 plus, and Q0 plus. So clock number 0, and the input is Q1 XOR with Q0. I mean, this is the inputs. The input is Q1 XOR with Q0. So initial state in this one, it is given 1001. Guys, please answer this. It should not take much more than 1 minute. So initial state is 1001. We haven't applied any clock. So clock is 0. So yes, somebody responded with 8 and your answer is 8. It is correct. So initially, we haven't applied any clock. We haven't given any input. So I'm putting a cross. This is the state. So then the input is Q1 XOR Q0. So I have to always do XOR of this and this column. So 0 XOR with 1 is 1. Then I'm giving the first clock. So this one will be shifted here. This one will be shifted here. This is 0 and this is 0. 0 XOR 0 is 0. So I'm giving the second clock. So you get 0 here. You get 1 here. You get 1 here. You get 0 here. 1 XOR 0 is, you get it is 1. So you give the third clock. 1. This is 0. This is 1. And this is again 1. So 1 XOR 1. That is 0. So you give the fourth clock. So this is 0. This is 1. This is 0. And this is 1. So 0 XOR 1 is 1. You give the fifth clock. You get your 1. You get 0. You get 1. You get 0. But I have to continue this unless until I get all these are 1, 1, 1, 1. So again, 1 XOR 0 is 1. I'm giving the sixth clock. It is 1, 1, 0, 1. Again, 0 XOR 1 is 1. I'm giving the seventh clock. This is 1, 1, 1, and 0. 1 XOR 0, again 1. Eighth clock. This is 1, 1, 1, and 1. So here I'm stopping, right? So I got 1, 1, 1, 1. After how many clock? 8 number of clock. So the answer of this question is 8. So from shift registers, okay, this is the only model questions you can expect in the GATE exam. So of course, as I said in the first class, skill-based questions, you need to have your own brain, right? Nobody can help you. But what is our intention is, if the regular model questions which are being asked in the GATE exams in the past history, so if that comes, you shouldn't be missing that. So my purpose is to cover up all those models. So if you go through our handbook, so these are the various configurations in SISO. So this is what information you need. So here, the information that somebody needs is to store a n-bit number, we need n number of clock pulse, and to take out, we need n minus 1 number of clock. Okay. To store, we need n number of clock. To take out, n minus 1 clock. In case of SIPO, serial in parallel out. Okay. So in this, you need n number of clock to store and 0 number of clock to take out. Okay. Next is in PIPO, you need only 1 clock to store, you need 0 clock to take out. And in the PISO, you need 1 clock to store and you need n minus 1 clock to take out. So these data, like although in GATE exam they haven't asked, but who knows, like if they may frame some match the following kind of cases, in that case, this information might be helpful. So the next questions I would like to take is, which is from the counters. Okay. So this is one model questions. Okay. So although this is, it looking a bit I mean, it looks like it's a lengthy questions, but these questions will give you a lot many informations. Okay. So intentionally, I have taken these questions. The question is obtain the overall mod number of the counter given below. Also find the output frequency of each counter. So you need to obtain the overall mod number of the counters. I mean, and what is the output frequency of each counters? Okay. So for your informations, you should be knowing a n-bit Johnson-Ning counter is a mod 2n counter. A n-bit ripple counter is mod 2 to the power n counter. Mod 12 counter is, any mod n counter is n counter. So 3-bit ring counter. So n-bit ring counter is mod n counter. 2-bit ripple counter is, it is again 2 to the power n, mod value to the power n. 2-bit parallel counter, it is again 2 to the power n. So these are some of the standard informations. Remember, so here it is 3 bits, 4 bits, these all are given. If I assume this 3, 4, 2, etc. n, so this is what is the standard information. Say n-bit Johnson-Ning counter is a mod 2n counter. N-bit ripple counter is mod 2 power n counters. And n-bit ring counter is mod n counter. N-bit ripple counter is 2 power n. Again, n-bit parallel counter is also mod 2 power n. So it's a 3-bit Johnson-Ning counter. So its mod value is 6. 3 into 2 is 6. 4-bit means 2 power 4 is 16. Mod 12 is mod 12. 3-bit ring counter is mod 3 counter. 2-bit ripple counter 2 power 2 is 4. And this is also 2 power 2 is 4. So you know the concepts, like whenever you have the individual counter structures, and if they are connected in cascade, then the overall mod number is product of their individual mod number. So what is the mod number of the overall structure? The answer is 6 into 16 into 12 into 3 into 4 into 4. You can take a calci and you can get it. This is what is the overall mod of the counters. Obtain the overall mod number of the counter. So this will be the answer. Find output frequency of each counters. The logic is very simple. If this is what is my Fin, so what is this? If I ask you, then the input frequency divided by the mod number. Input frequency is Fin, mod number is 6. So it is Fin by 6. If I ask you what is the frequency here, so the input frequency, this one now, Fin by 6. So Fin by 6 is the input frequency divided by this mod number, which is 16. So this is your 16. If I ask you what is this, so the input frequency is Fin divided by 6 into 16 divided by its mod number is 12, and so on and so forth. So you can find the frequency of each counter this way. Hopefully this logic is clear, right? And here, let us answer these questions. Okay. The question here is 55296. Okay, great. So this is the question. So this model question, I'm putting here 3 star. Okay. So this is very frequently this question is asked. So obtain the counting sequence Q1, Q0 for the following counter. What is Q1, Q0 for following counter? Assume the initial state is 1, 1. Assume the initial state is 1, 1. Obtain the counting sequence of this counter. So tell me, and I'm adding one more question here. Okay, if clock pulse are applied, then the value of Q1, Q0 is this. If 200 number of clocks are applied, then what is the value of Q1, Q0? So how do you answer? So the way to obtain such to solve such kind of question is you make a column for the present state. Then the next column is for flip-flop inputs. Okay. And next one is for the next state. So present state is Q1, Q0. Flip-flop input is J1, K1, J0, K0. Next state is Q1 plus and Q0 plus. Okay. So then what I'm doing is, so if you observe what is connected to J1 and K1, so J1, so this is nothing but this is Q0 complement because this line is coming from here. Same is the story for K1 as well. J0, if I ask you, so this is your Q1 complement, and this is anyway, it is given here 1. So I have observed these circuits, and here below J1, I'm writing here this is Q0 complement, K1 also Q0 complement. This I'm getting from here, okay? And J0 is Q1 complements, and K0 is constantly 1. So what I'm doing is, first let me write the corresponding combinations of this Q1, Q0. There are 4 combinations possible. J1 is Q0 complement, so complement of this column. So you get here 1, 0, 1, 0. You again get here 1, 0, 1, 0. This is Q1 complement, that is 1, 1, 0, zeros, and here it is 1, 1. So what is the information that you need is, you know the corresponding flip-flop inputs, you know the present state. Now you need to have the next state. You know the flip-flop inputs, you know the present state, you need to have the next state. So how do you solve it? So 1, 1 is the present state, means next state is 1, the complement of the previous state. If the input is 1, 1, then Q plus equals to Q complements. So Q is 0, so you get its complement. 0 complement is 1. Here also it is 1, 1. 1, 1 means you again get the complement of the previous state. So this state is 0, you again get here 1. 0, 0 means it will hold the previous state as per the JK flip-flop property. 0, 0 if the input means the present state is 0, so it will be maintaining 0. 1, 1 means it will be complementing the previous state. So 1 on the input means complement of previous state, 1 complement is 0. 1, 1 means again it will complement this. So 1, 1 means it will complement 1 means it is 0. 0, 1 means it is 0. 0, 0 means it will maintain the previous state, which is 1. 0, 1 means it is 0. So the counting pattern, if I ask you, what is the counting pattern? So here you see carefully, assume the initial state is 1, 1. That's what is information given. So if I observe, if the state is 1, 1, what is the next state? If 1, 1 is the present state, the next state is 1, 0. So from 1, 1, it is going to 1, 0. And if 1, 0 is the present state now, so from 1, 0, it is going to 0, 0. And if 0, 0 is the present state, so the next state is 1, 1. Next state is 1, 1. See here, 1, 1 to 1, 0, 1, 0 to 0, 0, 0, 0 to 1, 1. Again 1, 1 to 1, 0. This is the cycle. So 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0. Okay. So this is what is the pattern, counting pattern. So if I ask you what is the mod number, so if I ask you what is the mod number, so it's a mod 3 counter, because in the counting cycle, you have 3 distinct states. So it's a mod 3 counters. So if it is a mod 3 counter, okay, what does it mean? If it is a mod 3 counter, what does it mean? It means in every integer multiple of 3, the present state will repeat. I mean, if the present state is 1, 1, so if I'm going with any integer multiple of 3, like 3, 6, 9, 12, 15, or 99, like this, any multiple of 3, you'll again get it is 1, 1 only, because the present state is 1, 1, initial state. So same 1, 1 repeat on all the integer multiple of 3. That means if this is 3, so in every k value, if k is integer, in 3k, you are going to get the state 1, 1. So what is the number which is nearest to 200? So 199, no, 120, 198. Yeah. So 198 is integer multiple of 3. So in 198th clock, so the state is 1, 1. 199. So after 1, 1, we are going to get it is 1, 0. And in 200, so the next state from 1, 1, 0 is 0, 0. So on the 200 clock, what is the state means? It is 0, 0. How somebody is saying 0, 1? It is not 0, 1. It is 0, 0 only. So in such kind of questions, okay. So this kind of questions you can expect in the upcoming GATE exam, okay. So the state will be given and they'll be giving after these many clock, what is the corresponding state? So they will ask you. So in that cases, you have to observe the corresponding circuit diagram properly. Okay, by observing the circuit diagram, okay, you obtain the counting cycle. From the counting cycle, you'll get the idea of the mod number. And once you get the corresponding mod number, okay, then if you know the initial state, you can get what the state in the desired clock. Like 200, we are getting it is 0, 0. And here is the last questions from the sequencer circuit. So this question is basically, I can say, counter analysis. I mean, this question, okay, which is solved now. So why we are calling it is counter analysis? A counter circuit is given. We are analyzing it. How many, distinct states it is having? What is the mod number? These that we are just finding out. Okay. So, and the second model of question is called the synthesis-based questions. Like in this case, so instead of giving the circuits, so they are giving us the counting cycle. So for the given counting cycle, we have to design the circuits. So this is what is the one model of the questions, right? So again, we have some predefined steps for this. So if you follow that, you can easily answer them. So let me show you this question again. I have taken from our handbook only. So the question is, or the set of steps that somebody need to follow is like this. Yeah. See, synchronous counter design. Okay, design a synchronous counter. This is the question we have taken. So these are the set of steps actually. So write the combination of the present state. Step 1. By observing the desired sequence, write the next state respective to corresponding present state. Use excitation table of the flip-flop and fill up the flip-flop input column. Solve for flip-flop input in terms of present state and implement the circuits. So these are the 4 steps. So if you want, I'm just copying it. So while explaining you, I may use these steps. So where should I paste? Yeah, let me paste here. So what is the first step you're saying? First step is saying write the combination of the present state. So this is what? Write the combination of the present state. Okay. So in this case, what I'm doing is I'm making a table. So where I'm writing this is, so let me write here. So in one table, I can finish my job. Present state. So present state, here I'm writing this is Q1 and Q0. So the next step, okay. So the next step is next state. So next state, that is your Q1 plus and Q0 plus. And based on this, we'll be finding what is the flip-flop inputs. So clearly from the given data, we need 2 flip-flops. So the first bit is with respect to D, second bit with respect to T. So you need 2 flip-flops. I mean D1 and D0 if I'm going with D flip-flop. Similarly, T1 and T0 if you go with T flip-flop. Abhishek is asking, will COVID affect our exam dates? As of now, no such confirmations. But yes, if the severity of the pandemic is so horrible, then yes, there is chance. Everything is subjected to condition only. Nobody can tell now. Even some of the state governments, I'm observing, they are giving the notice tomorrow school will open, and again in the morning time itself in the news they're saying, okay, minister has cancelled. As of now, it is it is not going to open. Okay, I mean it is till further notice it will be closed. So like that. So don't be in the comfort zone. Like, okay, I'll get some 15 days or 1 month of time in that way. You don't think that way. You assume your date is the fix. Accordingly, you prepare. So present state. Okay. So the first step is write the combination of present. We have written that. By observing the desired sequence, write the next state with respect to corresponding present state. Okay. So many cases are in West Bengal, schools and colleges are closed. Yeah. I know in West Bengal it is closed, and in my place also it is closed. The second play, by observing the desired sequence, write the next state with respect to the corresponding present state. So here I'm writing the present state combination 0, 0, 0, 1, 1, 0, and 1, 1. So from 0, 0, I want to go to 1, 1. So if the input, I mean the present state is 0, 0, so next state is 1, 1. Next, if the present state is 0, 1, okay, so I need this one, right? If the present state is 0, 1, what is the next state? So if the present state is 0, 1, the next state is 1, 0. Next, if the present state is 1, 0, next state is 0, 0. So if it is 1, 0, it is 0, 0. And if the present state is 1, 1, the next state is 0, 1. So by observing this counting pattern, from 0, 0, I want to go to 1, 1. So from 0, 0, I'm writing here 1, 1, okay? Then from 0, 1, I want to go to 1, 0. So if it is 0, 1, here you see I'm writing here 1, 0. From 1, 0, I want to go to 0, 0. If it is 1, 0, you can see here I'm writing it is 0, 0. And from 1, 1, I want to go to 0, 1. So 1, 1, I have written here 0, 1. Isn't it? So you know the present state, you know the next state. Now you have to get the corresponding flip-flop inputs. So present state is given, next state is given. If you want to get the flip-flop input, which table you have to use? You have to use the excitation table. That to be because here we have the corresponding D flip-flop and T flip-flop. So you need to have the excitation table of the D flip-flop and the T flip-flop. So for that purpose, I am coming here. So here, this is the D flip-flop excitation table. And similarly, coming to T flip-flop, this is the excitation table. Isn't it? So how do you fill it up? So if you see the first one, so let us first do for D flip-flop, I mean for these segments, and then we'll go into the T flip-flop. So let me fill up this D and then we'll go to T. So how do you get D1? By observing Q1 and Q1 plus, I'll be getting D1. Later for T flip-flop, we'll be getting D1. Similarly, by observing Q0 and Q0 plus, I'll be getting the D0. Later, we'll be getting the T0. Okay. So Q1 and Q1 plus. So you can see a 0 and 1. So in case of D, if the input is 0, 1, so you see here, 0, 1 means it is 1. So here I'm writing this is 1. Similarly, by observing Q0 plus, this is also 0, 1. So here also you'll get it is 1. Next, again 0, 1. 0, 1 means it is 1. But next is 1, 0. So 1, 0 in the D flip-flop. 1, 0 in the D flip-flop. If 1, 0, present state, next state, this is 0. So I'm writing here, this is 0. Okay. So 0. Okay. Then 1, 0 again. So 1, 0. So 1 and 0. So 1, 0 means again it is 0 only. Similarly, so for 0, 1, we have written it is 1. For 1, 0, how much you get? So 1, 0, it is 0 only. So I'm writing here 0. Then you have 0, 0. So if it is 0, 0, so the first row says it should be 0. And if it is 1, 1, the last row says it is 1. So this is your 1. So same story you can repeat for the T flip-flop by referring this excitation table of T flip-flop. Okay, see. So again, 0 and 1. So 0 and 1, this one. So you get here 1. Then again, this is 0 and 1. So you again get here 1. 1 and 0. So if it is 1 and 0, you again get it is 1. So I'm writing here 1. Then 1 and 0, you again get here 1. Similarly, again 0 and 1, you get here 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0. Hopefully everything is fine. All of you are getting the same pattern or something else? All of you are getting the same, right? So this is what the step we have seen. So the first step, right combination of the present state. Okay, we have done it. By observing the desired sequence, write the next state corresponding. This we have done. Using excitation table of flip-flop, fill up the flip-flop input column. This also we did. So now we are left with the last step. Solve for flip-flop inputs in terms of the present state and implement the circuits. So what the last step is now telling us is, so the last step is telling us, one second. Yeah, the last step is telling us, so solve for the D1 in terms of Q1, Q0. Similarly, solve for D0 in terms of Q1, Q0. Solve for T1 in terms of Q1, Q0. Similarly, solve for T0 instead of, in terms of Q1, Q0. So D1, if I check, okay, these are the two rows that we should concentrate, that is 1 and 1. So D1 in terms of Q1, Q0, if I write, so this is your Q1 bar, Q0 bar, plus Q1 bar, Q0. So for this one, you get Q1 bar, Q0 bar. For this one, you get it is Q1 bar, Q0. So if you simplify this, you get it is Q1 bar. Similarly, D0, if I ask you, so you can see, so this is one, combination, and this is one combination. That is Q1 bar, Q0 bar, plus Q1, Q0. So which is Q1 XNOR with Q0. T1, if I ask you, is 1, because for all these it is 1. So T1 is constantly 1. And T0, if I ask you, so the first two rows, so it is your, again, like this only. So here also, this is your Q1 bar, Q0 bar, plus Q1 bar, Q0. So if you simplify this, you are getting it is Q1 bar. Okay, so this is what the design part. But what we have designed, actually, design in the sense, D flip-flop if you are using. So I'm taking here 2 D flip-flop. So what are the name I should give? D1 and D0. This is your Q1, Q1 complements, Q0, Q0 complements. So I'm just designing this synchronous counter. So all of them are triggered by the same clock source. So D1 should be connected to Q1 complements. So D1 is connected to Q1 complements. And D0 is connected to Q1 XNOR with Q0. So here I'm making a XNOR gate. One of the input is coming from Q1, other one is coming from Q0. Okay, na? One is coming from Q1, other is coming from Q0. So it is Q1 XNOR with Q0. So this is what is the corresponding circuits. And for T flip-flop, if you want to design, again the same way. So you have 2 T flip-flop, namely T1, T0, Q1, Q0, Q0 complement. This is Q1 complement. So what is T1? T1 is 1. What is T0? T0 is Q1 complement. So both of them are through the same clock source. So this is what the corresponding answer. So such kind of question also you can get. So if this is what is the pattern, what should be connected to D1, what should be connected to D0? Like that they will set the options. What should be connected to T1, what should be connected to T0? Like that they will set the options. Okay, so this is what about your sequential circuits. And through this couple of questions, so almost all concepts of sequential circuits I have covered. Thank you. That's all for today. Hopefully the session is helpful to you. And once again, okay, so this is the right time to write the test series. So please don't misuse your time. Thank you. I'm stopping here.